presenter today for this webinar, an introduction to inspection and testing for cathodic protection systems. Okay, Jared asks if I'm speaking. Can you hear me on the audio? Hello? Yes, I can now. Okay, all right, good enough. Okay, so an introduction to inspection and testing for cathodic protection systems. Cathodic protection is really a subset of corrosion protection. Your objective is corrosion protection, and you've got two tools that you can use to control corrosion. One is coatings and the other is cathodic protection. And you'll almost always use both of them on projects. When I'm talking about this, I'll be usually talking in terms of something buried in the ground, a pipeline or a tank, something like this. But another common corrosion protection situation involves underwater items. Again, something that's in the water. Now, with cathodic protection, what you're really doing is you're constructing and managing over the life of the project an electrical circuit, a circuit that electrical current flows in. And the basic components of an electrical circuit are an anode, a cathode, typically an electrical conductor like a copper wire connecting the anode and the cathode, and then the soil, or it could be water. The soil is part of the circuit. It does conduct electricity not real well, but it does. So your circuit consists of anode, copper wire, good conductor, and cathode, and then the electrode or the electrolyte. And what you are doing is protecting the cathode. That's why it's called cathodic protection. It's not called anodic protection. Now, the bad guys in this picture are negatively charged oxygen ions that are in the soil. Let me see. Let me check my chat box here. Let's see. Please type your questions in the chat box, blah, blah, blah. Okay, and let's see. All right. I'm not really very familiar with this Zoom system. I have used it quite a bit in the past, but it's still kind of a little bit of a learning experience for me. So getting back to the bad guys in this picture, the bad guys are negatively charged oxygen ions that are in the soil. And they get there in mysterious ways, chemical processes, biological processes, but they're out there. And as you will recall, opposites attract. And so the negatively charged oxygen ion in the soil is looking around for a positively charged ion to bind with and form a stable compound. And your cathode is in our industry, the business we're in, we're almost always talking about our cathode being some form of iron, cast iron, steel, et cetera, et cetera. And so the negatively charged oxygen ion looks around and it sees your positively charged iron ions over there in your structure that you're protecting. And it wants to, and does, migrate over to your structure, which is the cathode in the electrical circuit, and bind with the iron to form a stable compound. And that stable compound is ferrous oxide or ferric oxide, and that's rust, that's corrosion. With cathodic protection, however, again, you also will have used coatings on your underground structure, your pipe or your buried tank or whatever. And what you want to do is construct an electrical circuit that will result in the anode in the circuit exerting a stronger force on the negatively charged oxygen ion, and it will attract the negatively charged oxygen ion over to the anode, and it will bind with an ion in the anode, which is some kind of metal. Essentially, it's probably going to be magnesium or zinc or possibly aluminum. As a result, then you get a zinc oxide or a magnesium oxide formed, which is a stable compound. And so the negatively charged oxygen ion has left your protected structure, your cathode, alone. And as a result, it's the anode that corrodes away, the zinc rod or the magnesium rod, whatever it is you stuck in the ground. And it leaves your structure alone. So that's fundamentally something that is always happening with cathodic protection. And the anode corrodes away over time, and at some point in time in the future, you're going to have to go out there and replace those anodes. And the purpose of inspection and testing for cathodic protection systems, this is what I refer to as the babysitting for the cathodic protection system. What you need to do is to routinely inspect and conduct testing on your cathodic protection system to ensure that the system is working, that this electrical circuit hasn't broken down in some way, and the electrical circuits do break down. The corrosion takes place in whatever you've put in the ground, and there can be earth movement and movement of the groundwater table, and the electrical circuit that you have constructed is broken. And if it's broken, then you can't have a current flowing in it. And so the purpose of inspection and testing is to assure that that your system is functioning properly, and that your anodes are still functioning properly, because they can deteriorate in the ground. So the cathodic protection systems need to be checked probably around once every 2 to 4 years to make sure that they are operating properly. The testing of the systems, the cathodic protection systems, is relatively straightforward, but special equipment is necessary to perform the tests. Each cathodic protection system has a test box installed and you'll see some schematics here shortly, to facilitate checking the system. Anodes are a very low Sorry, I've been talking away here. This shows how unfamiliar I am with this Zoom system. I'm sorry, I had my audio muted. Well, backing up just a little bit, a cathodic protection system needs to be checked around once every 2 to 4 years to make sure that it is still functioning properly, that there hasn't been any breaks in the electrical circuit that you have constructed, and that the anodes are still functioning. That is, they have not corroded away and are no longer down there. And the testing and the monitoring of the cathodic protection systems is what we're talking about here today. Now, there are 2 types of cathodic protection systems. One, excuse me, just I've got to. Okay, I'm back. Here is just by way of introduction is a little bit about me and I'm doing for the last few decades. I have not been doing nothing but cathodic protection and corrosion protection projects for my career. Let's see the questions. Are slides changing? It sounds like, but it does not seem like you can hear them. Okay. All right. Are we still on slide 1? Okay, I'm moving the slides now, so hopefully that takes care of that. Okay, and chat. Okay. All right. Anyway, this is a little bit about me, and I have always been a broadly based designer, not just doing nothing but cathodic protection. I got registered in a few different things along the way, but I'm basically a mechanical engineer. So that's me. And again, I apologize for the clunkiness that I'm having as a result of this Zoom system. Here's what I'll be talking about today: is an overview of testing and monitoring of cathodic protection systems to assure that they are continuing to protect your structure, which is the cathode in the electrical circuit that we've constructed. I'll talk a bit about inspection procedures and criteria, the applicability of the testing procedures to, depending upon what your protected structure is made out of. In the vast majority of cases, it's going to probably be made out of iron, but you might have a copper pipe or something like that. We'll talk about criteria and other considerations, and then alternative reference electrodes, which we'll get into later, what a reference electrode is, and then the testing. The cathodic protection systems typically, now again, you've got two tools available to help you protect your structure that's buried in the ground or possibly is underwater. One of them is coatings and the other is cathodic protection. And the coatings will protect a significant amount of your structure, somewhere in the range of 90 to 95%, but there's always going to be a 5 or 10% of the surface area of your protected structure that is not protected by the coating because the coating has deteriorated. And it's this unprotected portion of your structure that you are protecting with the cathodic protection system. The two types of cathodic protection systems are galvanic or sacrificial anode, and the other kind is impressed current. Again, the whole big picture of what you're doing with cathodic protection is constructing an electrical circuit, anode, copper wire, good conductor connected to the cathode, and then the current comes back through the electrolyte, which is the soil, or it could be water in an underwater application. And the cathodic protection systems need to be monitored to assure that they are continuing to function properly over time, because things change. Groundwater levels bounce up and down. You can have earth movements that will twist the wires and perhaps cause the connections to break. So the cathodic protection systems need to be checked around every 2 to 4 years. Testing the system is relatively straightforward, but special equipment is necessary to perform the test. Now, this is a simple picture of a test installation. Hang on just a sec here. You've got your buried pipe in the ground, and you have a test box with leads going to the pipe and to the anode, the pipe being the cathode. The tests that you perform typically, first of all, there's the pipe to soil voltage potential, and this is done by measuring the voltage between the protected structure, the pipe, and a standard electrode which is called a copper sulfate half cell that is stuck in the ground. And so you're measuring the voltage difference between the protected structure and the electrolyte, the soil. This copper sulfate half cell, it's a kind of like a half battery cell, which when it's placed in contact with the ground and connected through a voltmeter to a metal in contact with the ground, it'll produce a comparative voltage for the metal to soil. The comparative voltage for example, a corrugated metal iron pipe that is protected should be about 0.58 volts or higher. This is a key guideline around 0.8 to 0.85 volts, because that's the electromotive force that is pushing the bad guys in this scenario, the negatively charged oxygen ions, pushing them away from your cathode and pushing them towards the anode, so that it's the anode that gets corroded and not your cathode, which is what you are protecting. The testing, you need to test for the first the pipe to soil voltage potential, because that has to be 0.85 volts negative or more. And if it isn't, that means that your structure is not being adequately protected. That 0.85 or 0.80 millivolts is a key indicator of whether or not the system is functioning properly. The next case or test is for continuity of the pipe, that is has the pipe is in the electrical circuit that you've constructed, and so it has to be continuous. In other words, have no breaks in it, and it's acting just like a big wire, and it's the pipe needs to have its continuity tested, and so that is the let's get another slide up here. Okay, this is a schematic indicating the where you put a voltmeter in the circuit that is running from the anode through the electrical wires, and you put a voltmeter, volt ohm meter in the circuit to take the measurement of the voltage. And then the other end of the circuit is connected to the thing you're protecting, the pipe in the ground. And so this test shows if the pipe is making a continuous circuit, and it's the test, it will show if either of the wires between the test box and the pipe is broken or has a bad connection to the pipe. Ohm readings of less than 3 ohms indicate continuity. Now, the next test is the third test is testing the voltage output of the anode. Now, in a sacrificial anode system, the voltage you get is a function of the electromotive potential of iron, your protected structure, and the electromotive potential of the metal that you select for your anode. Typically, it's going to be magnesium or zinc, maybe aluminum. And this is simply taking advantage of the fact that different metals have different electromotive potentials. And so if you select the metal for the anode correctly, which means magnesium or zinc, it is inherently going to exert a stronger electromotive attractive force on the negatively charged oxygen ion in the soil, which is the bad guy in this picture. And so this third test is testing the voltage output of the anode, of whatever metal you have selected. And this test is a comparative one using, again, this standardized copper sulfate half cell. And the normal anode potential voltage will be in the range of 1.4 to 1.6 volts. And that's just because of the inherent properties of the anode metal, zinc, magnesium, etc., as compared to the metal in your protected structure, which is iron in the vast majority of cases. So the normal anode potential voltage that you measure with this test needs to be in that range of 1.4 to 1.6 volts. If it is, if the voltage that you read is in the range of 0 to 0.3 volts, that means something's broken. A wire is broken or a connection is broken. So identifying those breaks so that they can be repaired is what you are doing. Now, let me, by the way, I don't think I mentioned the format for these webinars is I press on with the presentation for 50 minutes, and then we take a 10-minute break so people can check their emails and do things like that, and come back and do another 50 minutes, 10 minutes, 50 minutes, 10 minutes. Now, this is just a 2 PDH webinar, so we'll just go through that cycle twice. Okay, now here we see a test set up. You've got your protected structure, which is the pipe, which is the cathode, and you've got this test box that typically is installed, and that allows you to conveniently install a volt ohm meter in the circuit, and then the other end of the other wire from the volt ohm meter is connected to the anode that you have stuck in the ground. This is going to be magnesium or zinc, and you are then measuring the voltage between the anode and the between the electrode, the copper sulfate half cell. That one end of the wire there, I misspoke myself. That is not the anode, a test electrode. And so this is the fourth test, which is measuring the current flow from the anode to the pipe. And this could vary from 5 milliamps to 300 or more milliamps, depending on pipe area, soil resistivity, and soil moisture. And that, of course, is because the soil is part of the electrical circuit that you've constructed. A current flow larger than the design current usually means the pipe is protected to a higher level than needed, and this is a waste of the anode, because the anode's going to corrode away faster. You're going to have to go out there and replace them more frequently. This will result in a reduced anode life. If the current is more than 1.3 times the design requirement, a resistance should resistance should be added to the circuit to extend the life of the anodes. And this is typically done with a length of special high resistance wire between the connections in the test box. Now let's press on. Okay, yeah, we really already covered this. A comment here is you can't possibly assimilate to any degree this this much information, highly technical information, in a brief little 2-hour webinar. You need to get a copy of these PowerPoints and then sit down when you've got some time to go through them and review what I've been saying and get comfortable with the topic. So is the test setup measuring the current flow from the anode to the protected structure. So you've got your electrical circuit, which is connected a wire to the anode that you've selected, zinc, magnesium, or whatever, and a copper wire runs up to the test box, and you install a volt ohm meter connection to the connections in the test box, and then the conductor, the other conductor is connected to the structure being tested or that you're protecting, a pipe, underground pipe or tank. So to conduct these testing operations, there's a bit of special equipment that's needed. In a typical situation, you'll probably need 200 to 300 feet of a rubber coated number 18 AWG wire on a reel. You'll need a volt ohm milliamp meter with DC volt ranges of 0 to 2.5 or 3 volts, milliamp ranges of 0 to 500 with 2 lower maximum deflection ranges, ohm ranges with expanded scales in the 1 to 5 plus or minus ohm range. You'll need this standardized copper sulfate electrode with a porous plug. The half cells are available from any supplier of corrosion engineering testing equipment. This stuff is all available commercially. And then 2 or 3 extra 4 to 8 foot leads of number 18 AWG wire with small alligator clips. Now, let me see here. Okay, the inspection procedures then used either separately or in combination the intent is to indicate whether adequate cathodic protection of a metallic piping system has been achieved. In other words, do you have enough current flowing in this electrical circuit that you have constructed such that the negatively charged oxygen ions will be attracted to the anode rod that you've got in the ground, and therefore leave your cathode protected structure alone. Now, the effectiveness of the cathodic protection or other corrosion control measures like coatings can be affirmed by visual inspection, going out and looking at the protected structure. Is it corroding? Going out and looking at the anodes. Are they being corroded away too fast? If they are being corroded away too fast, they may, in essence, break in two, which reduces their effectiveness. And that's one reason is you're doing this inspection and testing. Some of the methods, visual inspection may not be practicable because you can't get to all parts of the protected structure or all parts of the anodes. As part of the inspection, you may well need to undertake some digging, some excavation. So when you are excavating, the pipe should be inspected for evidence of corrosion and or coating conditions. Again, you've got two tools, coatings and cathodic protection. And if the coating system is heavily deteriorated, that means that you're probably going to have to increase the current flowing in the cathodic protection system to compensate for the larger area of unprotected structure, unprotected by the coating system. These criteria that I'm talking about here, they've been developed over many years in the field and in laboratory undertakings, and they've been verified by evaluating the data obtained from successfully operated cathodic protection systems. Situations may exist where a single criterion for evaluating the effectiveness of cathodic protection may not be satisfactory for all conditions, and often a combination of criteria is needed for a single structure. A piece of information that you gather from these inspections is a corrosion leak history, and this is a valuable piece of information. In other words, how have similar projects with similar in similar soil conditions, how have they performed in the past? You determine how they've performed in the past by going out and looking at them and seeing if they're if the cathode, your protected structure, is heavily corroded or not, and are the anodes still intact. So the performance, the leak history of the similar structures buried in similar soil conditions is a legitimate piece of information to for you to use. Now, these now how do we apply these inspection and test procedures? the recommended practice is to serve as a guide for establishing minimum requirements for control of corrosion on the following types of systems. First of all, new piping systems. Corrosion control by coating supplemented with cathodic protection or by some other proven method, which there really isn't any, should be provided in the initial design and maintained during the service life of the piping system. In other words, the corrosion protection system needs to be part of the original design. And that isn't always the case, because there are a lot of things out there that are buried in the ground, pipes and tanks and this sort of thing, that where corrosion control measures such as coatings and cathodic protection were not part of the original design. So you have to go out and evaluate those existing buried tanks and buried pipelines. And in this day and age, keep in mind, as far as the inspections of whatever, of your cathode, your buried pipeline, take advantage of the fact that there are now commercially available these pigs, which is a little propelled TV camera, basically, that will inspect the inside of pipelines and give you a more complete picture of how effective the cathodic protection and corrosion protection measures have been in preventing internal corrosion. Now, in existing coated piping systems, let's see, let me back up here just a bit. In the with existing coated piping systems, cathodic protection should be provided and maintained unless investigations indicate that cathodic protection is not required. Now, there are some soil conditions are more corrosive than others, and we won't go into how that is determined, but some soil conditions are more corrosive than others, and in the less corrosive soil environment, may in fact not be necessary to spend the time and money on a cathodic protection system. It may be in these less corrosive soil environments that just coatings can be expected to perform adequately long term. With existing bare piping systems, studies should be made to determine the extent and rate of corrosion on existing bare piping systems. When these studies indicate that corrosion will affect the safe or economic operation of the system, adequate corrosion control measures should be taken, coatings and cathodic protection. Special conditions sometimes exist where cathodic protection is ineffective or only partially effective, and such conditions may include elevated temperatures, disbonded coatings, for whatever reason the coating system has deteriorated, thermal insulating coatings, shielding, such as for electromagnetic radiation, bacterial attack can be encountered, and unusual contaminants in the electrolyte in the soil. Deviation from the recommended practices may be warranted in specific situations, provided that corrosion control personnel in responsible charge are able to demonstrate that the objectives expressed in the recommended practice have been achieved. Okay, the criteria that are being described in here, these all come from the technical literature produced by NACE, the National Association of Corrosion Engineers, and some of their selected publications, RPO 169, corrosion control of external corrosion on underground or submerged metallic piping systems, RPO 285, corrosion control of underground storage tanks by cathodic protection, and several others. And then let's see, I'm looking at my clock here. For steel and cast iron piping, corrosion control can be achieved at various levels of cathodic polarization. That is the negative, the voltage difference between the electrolyte and the cathode. In the absence, though, of specific data that demonstrate that adequate cathodic protection has been achieved, one or more of the following should be a guide. Let me. The target for your electrical circuit that you're constructing is to have a negative or cathodic potential of at least, again, the magical 850 millivolts with the cathodic protection applied. And that means if it's a sacrificial anode system, the anodes are in place and have been connected up. If it's an impressed current system, it's with the rectifier or source of DC current operational. This target potential of 850 millivolts is measured with respect to, again, this standard copper sulfate reference electrode contacting the soil, the electrolyte. Voltage drops other than those across the structure to electrolyte boundary must be considered for valid interpretation of this electrical measurement. Note that consideration is understood to mean the application of sound engineering practices to determine the voltage drops by methods such as measuring or calculating the voltage drop, reviewing the historical performance of the cathodic protection system, and evaluating the physical and electrical characteristics of the pipe and its environment. Specifically, the soil, is it a highly corrosive environment or not so highly corrosive? And then determine by inspection whether or not there is physical evidence of corrosion. A minimum of 100 millivolts of cathodic polarization between the structure, surface, and a stable reference electrode contacting the electrolyte. The copper sulfate cell is the electrode stuck in the ground. The formation or decay of polarization can be measured to satisfy this criterion. This criterion is not valid when bimetallic corrosion, such as when connected to copper grounding, is present. Okay, I'm looking at my clock here, and it's time to take our first 10-minute break. So let's do that and come back on the hour, and we will pick up here, and I'll have a few cautionary comments to make. So I'll see you all in 10 minutes on the hour. Okay, this is Paul Geyer. I'm back. Now, some cautionary comments here. Using polarized potentials less negative than 850 millivolts is not recommended for cathodic protection of pipelines when operating pressures and conditions are conducive to stress corrosion cracking. That's when stress induces cracks and then corrosion takes place within the cracks. So again, this is that magical guideline or rule of thumb that you want the cathode to be 850 millivolts negative when measured relative to the electrolyte. Also, the use of polarized potentials on coated pipelines should be avoided to minimize cathodic disbondment of the coating, because that can occur. Also the polarized potentials, the voltage that result in excessive generation of hydrogen should be avoided on all metals, particularly higher strength steel, certain grades of stainless, titanium, aluminum, and pre-stressed concrete pipe. Okay. Now with aluminum pipe, and of course, usually what we're dealing with in the industry we're in tends to be steel or iron or some form of it. But should you be utilizing aluminum piping for some reason, the following comments apply. A minimum of 100 millivolts of cathodic polarization between negative voltage between the structure surface and the reference electrodes stuck in the ground. So the formation or decay of this polarization can be used in this criterion. So a minimum of 100 millivolts if you're dealing with aluminum pipe rather than steel pipe. Couple of more cautionary comments. Excessive voltages, notwithstanding the minimum criterion, if aluminum is cathodically protected at voltages more negative than 1200 millivolts measured between the pipe surface and the standard saturated copper sulfate reference electrode contacting the electrolyte, the soil, and compensation is made for the voltage drops other than those across the pipe electrolyte boundary, it may suffer corrosion as a result of the buildup of alkali on the metal surface. Another cautionary note, with alkaline conditions, aluminum may suffer from corrosion under high pH conditions, alkaline, and application of cathodic protection tends to increase the pH at the metal surface. Therefore, careful investigation or testing should be conducted before applying cathodic protection to stop pitting attack on aluminum in environments with a natural pH in excess of 8.0, in other words, alkaline. With copper rating, a minimum of 100 millivolts of cathodic polarization between the structure surface and a stable reference electrode contacting the electrolyte. The formation or decay, whoops, got away from me there. The formation or decay of this polarization can be used in this criterion. With dissimilar metal piping, a negative voltage between all pipe surfaces and a stable reference electrode contacting the electrolyte, the soil, equal to that required for the protection of the most anodic metal should be maintained. A word of caution is with amphoteric materials, those which can form either a base or an acid, that could be damaged by high alkalinity created by cathodic protection and should be electrically isolated and separately protected. Other considerations, determining the voltage drops. Methods for determining the voltage drops should be selected and applied using sound engineering practices. Once determined, the voltage drops may be used for correcting future measurements at the same location, providing conditions such as pipe and cathodic protection systems, operating conditions, soil characteristics, and coating quality remain the same. Note that placing the reference electrode next to the pipe surface at the pipe electrolyte interface. A reference electrode placed at a coated pipe surface may not significantly reduce soil voltage drop in the measurement if the nearest coating holiday is remote from the reference electrode location. Sound engineering practices, when it's impractical or considered unnecessary to disconnect all current sources to correct for voltage drops in the pipe electrolyte potential measurements, sound engineering practices should be used to ensure that adequate cathodic protection has been achieved. Where practical, inline inspection of pipelines may be helpful to turn the present absence of pitting or corrosion damage. The absence of corrosion damage or the halting of its growth may indicate adequate corrosion control. Stray currents and stray electrical gradients, situations involving stray currents and stray electrical gradients may exist that require special analysis. Stray currents, that's when you have, say, several or more than one protected structure, pipeline or buried tank in close proximity to each other. And these stray currents are produced in the electrolyte, in the soil, and they can and do interfere with the cathodic protection system that has been installed in a nearby or adjacent pipeline or buried tank. I've been continuing to talk about the reference electrode, this thing you stick in the electrolyte in the soil, as being this copper sulfate half cell. But there are alternative reference electrodes. An alternate, it may be substituted for the copper sulfate electrode. A couple of commonly used reference electrodes are listed below, along with their voltage equivalent at 77 Fahrenheit to 850 millivolts, referred to a saturated copper sulfate reference electrode. Saturated potassium chloride, calomel reference electrodes, the guideline voltage is minus 780 millivolts rather than minus 850. And saturated silver or silver chloride reference electrodes used in seawater, 25 ohm per centimeter seawater, it would be minus 800 millivolts. Alternative metallic material or structures in addition to these standard reference electrodes, an alternative metallic material or structure may be used in place of the saturated copper sulfate reference electrode if the stability of its electrode potential is ensured and if its voltage equivalent referred to a saturated copper sulfate reference electrode is known and established. In testing, the voltage or potential measurements, cathodic protection systems must be tested to assess system function and troubleshoot inadequate performance. The potential measurement based on the theory of measuring an unknown potential by relating it to a known reference electrode is the principal test procedure used. A measurement is taken by connecting the high resistance voltmeter negative lead to the reference electrode, the half cell, the copper sulfate half cell, and connecting the positive lead to the metal that is being tested. A word of caution: if the voltmeter has a polarity switch and a D'Arsonval movement, that is a needle that deflects only in the positive direction, select negative. If there is no polarity switch, attach connections backwards, negative lead attached to the structure and positive lead to the reference cell to prevent damage to the meter, then interpret the positive deflection as a negative reading. There are 5 sources of error when taking potential or voltage measurement of a structure. These are the accuracy of the reference electrode, a voltage error, IR, current times resistance error, present when current is flowing, an anode gradient field present when current is flowing, contact resistance error when the reference electrode is not in good contact with the electrolyte, and the influence of foreign structures, that is mixed potentials. The accuracy of the reference electrode to prevent erroneous potential measurements. The accuracy of the reference electrode, that is the copper sulfate half cell, must be reliable. A valid tested reference electrode must be used to take all potential measurements. Temperature affects the potential of the reference cell. There is an increase of approximately 0.9 millivolts per degree Celsius or 0.5 millivolts per degree Fahrenheit. So a measurement of minus 0.85 at 21 centigrade, 70 Fahrenheit would read minus 0.835 at 4 degrees centigrade, 40 degrees Fahrenheit, and 0.865 at 38 centigrade, 100 Fahrenheit. To determine the accuracy of a reference electrode, multiple reference electrodes must be used. In practice, there should be one reference electrode maintained properly, which is not used in the field to check other reference electrodes against before they are used in the field. This reference electrode must be properly initiated and stored. Picture here of a copper sulfate reference electrode half cell, what they look like. Important. The metallic electrode must be cleaned thoroughly using non-metallic materials. Do not use metallic sandpaper, grinders, emery cloth wire brushes, knife blades, or any other metallic cleaning method. For example, aluminum oxide sandpaper will deposit particles of aluminum on the copper, or wire brushes will deposit particles of steel on the copper, thus changing the potential of the electrode. With regard to preparing the electrolyte solution, it must be fully saturated solution of copper sulfate. The half cell body must be thoroughly cleaned and rinsed out several times with distilled water before mixing the solution in the half cell. There should be approximately 1/3 the volume of copper sulfate crystals installed in the half cell, then the remaining volume filled with distilled water. With regard to testing to determine the accuracy of a half cell, use multiple reference electrodes. Using a reference electrode, measure the difference in potential to the half cell under test. Use a meter on the millivolt scale, place the two cells cone to cone, and measure the potential differences. Voltage, or IR, current times resistance drop error. There is an IR drop error caused by cathodic protection current flowing through the electrolyte, which is a resistor. This error is greater when the current is higher and when the resistivity is higher, when the distance from the reference electrode to the structure is higher, and on a well-coated pipeline when the distance to the nearest holiday is greater. An instant off or an IR free potential measurement will remove this error. This error is in the negative direction. For example, with the error, you may measure a minus 0.85 volt DC potential, and after correction for the error, you may actually have minus 0.75 volts DC. And here we have a simple picture of the voltage drop error IR condition. Anode gradient error. The voltage gradient of the anode causes an error when the anode is connected in the circuit during testing. That's with current on. This error is greater when the voltage at the anode is higher and when the distance of the reference electrode to the anode is shorter. The cathodic protection circuit resistance, the number of anodes, and the electrolyte resistivity affect the anode gradient field size. The anode gradient is larger when the circuit resistance is higher. The causes of high circuit resistance are high soil resistivity, low number of anodes, and anodes being spaced too close together. Figure 3 indicates an anode gradient error. Contact resistance error. Poor contact of the reference electrode to the electrolyte results in error. The contact resistance of the half cell to earth is problematic under rocky or dry conditions. Apply water on dry ground and or use a very high resistance voltmeter. Cathodic protection voltmeters should have selectable input resistance from 1 million to 200 million ohms. Normally, 10 million ohms is the selected scale. While taking a potential measurement, switch the input resistance to the next highest selection. Figure 4 indicates the contact resistance error. Next, potential voltage error. Error results when a potential measurement being taken on the structure is mixed with the potential of other structures also connected to the circuit being tested. This error can be significant when the coating on the structure being tested is very good and there are other structures in the area not isolated from the cathodic protection system. This error is present when the system being tested is not isolated and is greater when the condition of the coating is better. The distance to the nearest holiday is greatest. The distance of the half cell to the other structure is shorter when the coating of the other structure is worse or bare, and when the native potential of the other metal is less negative, that is more cathodic, such as copper. Figure 5 illustrates the mixed potential error. Now, some comments on the practical measurement of cathodic protection potentials. Test criteria selection. The method used for potential testing varies widely for different types of structures and for the different criteria used for evaluation of the potentials. Sometimes different criteria may be used for different areas on the same structure. The criteria selected depend mostly on the type of the structure, isolation / non-isolation of the structure, structure coating type and efficiency, the type of cathodic protection system, the soil resistivity, the amount of current supplied by the system, cathodic protection system, and the instrumentation available for testing. For sacrificial anode cathodic protection systems, generally, the criterion for sacrificial anode cathodic protection systems is 0.85 volts with the cathodic protection system on. If the voltage error must be compensated for usually by placing the reference electrode as near to the structure as possible, over the pipeline or tank, and as remote as possible from any sacrificial anode. This, combined with knowledge of the structure coating, the soil resistivity, the size and spacing of the anodes, and the anode current, is usually enough to determine the adequacy of the cathodic protection applied to the structure. If in doubt, or when potential readings are questionable, excavate to allow placement of a temporary reference electrode or permanent reference electrode as close as practical to the structure to further minimize any possible IR or voltage error. Um, Sacrificial systems are normally used in low soil resistivities on well-coated structures with a low current requirement. Recall the sacrificial anode systems are relying for the current in the electrical circuit you've constructed on the inherent difference in electromotive potential of different metals, steel versus magnesium as an example. And because of the very small driving voltage, which is under 1 volt, and have very small amount of current flow, if the dielectric strength of the structure coating is not good, the soil resistivity is relatively high, or the location or spacing of the anodes makes it impossible to measure the structure potential from the anodes, other criteria should be used or excavations made to the properly placed in order to properly place the reference electrode to obtain a valid potential measurement. For very small and well-coated structures, such as valves, elbows, and tie-downs, use the 100 millivolt polarization criterion. For all sacrificial systems, if the sacrificial system is designed to allow interrupting the current from all anodes simultaneously, the minus 100 millivolt polarization criteria could be used. The minus 0.85 instant off with the cathodic protection system not connected, not on. Criterion is usually not attainable in most soil conditions with sacrificial anodes unless the native potential of the structure is very high and or the soil resistivity is very low. The minus 0.85 volt instant off criterion should not be used for sacrificial cathodic protection systems except in rare cases. Use the 100 millivolt shift criterion or the minus 0.85 on criterion, considering the current resistance. For impressed current systems, the first consideration for determining the criteria to use with impressed current systems is the type of anode bed used. For distributed anode impressed current systems, the minus 0.85 instant off or the 100 millivolt polarization criteria should be used. The minus 0.85 on criterion should not be used. For structures with a high dielectric strength coating, the minus 0.85 instant off criterion may be the easiest to use, although the 100 millivolt polarization criterion can be used. For structures which are bare, poorly coated, or have a deteriorated coating, the 100 millivolt polarization criterion should be used. For remote anode impressed current systems, all criteria or a mixture of criteria may be used. If the anodes are truly remote from the test point, the electrolyte resistance is low, the dielectric strength of the coating is high, and the circuit resistance of the cathodic protection system is low, the minus 0.85 on criterion, considering IR voltage error, is sufficient. Okay. The test methods for the minus 0.85 on criterion. A single electrode potential survey is conducted using any high impedance or high input resistance voltmeter. 10 mega ohms or higher. The voltmeter positive is connected to the structure under test, and the voltmeter negative is connected to the reference electrode to display the proper polarity for analog meters, which only read in the positive direction. The leads must be connected backwards to get an upscale deflection, and the negative value must be inserted when recording the measurement. The minus 0.85 volts DC is measured to again, copper sulfate reference electrode half cell. Other types of reference electrodes must be corrected to the copper sulfate reference to use the minus 0.85 volt criterion. Figure 8, pardon me, figure 6 illustrates the single electrode potential survey. The test method for the 0.85 instant off criterion. For these criterion, the measurements of potential must be taken when there is no cathodic protection current flowing. The measure of the instant off, or the potential when the cathodic protection is not flowing, is required as the means of removing errors from the measurement. If the potential measurement meets or exceeds minus 0.85 volts DC in comparison to the copper sulfate reference electrode, using these methods, this criterion has been met. Other reference electrodes must be corrected to the factor for a copper sulfate reference to be valid under this criterion. With regard to the test method for the 100 millivolt polarization criterion, the test method for this criterion is exactly like the method for the negative 0.85 instant off criterion, with the additional requirement of either comparing the measurements to a native survey, potentials taken before the cathodic protection current was applied, or allowing for the measurement of the polarization decay. It's recommended that the native potentials be used to compare the instant off readings for the 100 millivolt polarization criterion. After the cathodic protection has been applied, the structure is polarized, and even after current interruption, considerable time may be required before the potential returns to the native potential value. Measuring polarization decay guarantees the proper shift, but may require considerably more current to polarize the structure to a level where the 100 millivolt depolarization would occur in a relatively short time. Testing with the instant off test method. The test method used for an instant off potential measurement is determined by the type of equipment used and the type of current interrupter used. Types of equipment include a normal high input impedance digital voltmeter may be used in combination with conventional current interrupters, manually synchronizable, at advanced synchronizable interrupters or advanced synchronizable interrupters, not pulse generators unless used as a conventional interrupter. A data logger which records potential measurements very quickly. Waveform analyzer may be used together with a pulse generator to calculate the off potential. A high-speed data logger and oscilloscope or similar very high-speed recording device may be used to analyze the unfiltered signal on the structure to obtain the potential of the structure when the DC output waveform is at zero current output. Few comments on the types of interrupters. The type of interrupter used depends on the number of rectifiers or DC current sources and the type of equipment used to perform the instant off measurements. Manual interruption of a cathodic protection rectifier using an AC power switch, rectifier circuit breaker, or other means is generally not recommended. The time to manually open and close contacts, coupled with interruption of the AC side of the circuit, does not provide accurate or repeatable measurements under many conditions within the first second of interruption, resulting in significant inaccuracies in the measurement obtained. Manually, manually synchronizable interrupter, this unit is similar to a high quality conventional interrupter and may be accurate to within 1/10 of a second in 24 hours, with the additional feature of synchronizing the interruption cycle with other like units. This is normally accomplished by using a supplied cable for temporarily connect two units together to start second, third, fourth, etc. units for synchronization of the interruption cycles of all units. It's made possible to interrupt several rectifiers simultaneously, to use various instruments to measure an instant off potential reading. They are usually portable, but could possibly be installed equipment with a portable unit used to synchronize the rectifier installed units. With regard to advanced synchronizable interrupters, these units are similar to a manually synchronizable interrupter with the means of synchronization controlled by some communication technology versus manually by cable connection, such as radio, computer connection, modem, or satellite transmissions. They are usually permanently installed, but portable units are also available. With regard to advanced synchronizable interrupters, these units are similar to the manually synchronizable interrupter with the means of synchronization controlled. With regard to pulse generators, the pulse generator can normally be used as a conventional current interrupter or as a standard pulse generator. They may be permanently or temporarily installed in the rectifier cabinet. They do not require synchronization when used together with the proper waveform analyzing equipment. If used for a conventional current interrupter, they are not synchronizable, but usually provide for user selectable interrupt cycles. The standard pulse generator is connected in series in the DC output, either positive or negative of the rectifiers, and produces a precisely timed zero current pulse that does not drift. AC supply voltage is used to power the pulse generator. Selectable input AC power units must be set for the correct AC supply voltage being used. Ensure the pulse generator is set to the proper voltage before applying AC power, or the pulse generator will be damaged. With regard current requirement testing procedures. Current requirement testing is conducted when planning a cathodic protection system installation to determine the type and size of the system required. If the system design requires isolation of the structure to be protected, that isolation must be accomplished prior to the current requirement test. The current requirement for a non-isolated structure does not give any indication of what the current requirement would be if the structure were isolated. Temporary systems are used to determine the effect of current applied on the potential of the structure being tested. Excuse me. Actual protection need not be accomplished to estimate the amount of current required. Portable rectifiers should be used together with temporary anodes, usually ground rods, or existing metallic structures to impress a test current to the structure. Vehicle batteries can be used, as well as spare rectifiers, DC generators, DC welding units, or rectifiers from other systems can be temporarily removed for use. For temporary local cathodic protection systems, they should be located in areas where the intended installation is to be located, if known. If not known, they should be located as remote as possible from the structure to be protected without any foreign structures in the area or the temporary anode bed, and without any foreign structure between the temporary anode bed and the structure to be protected. A word of warning: do not use any metallic structures for a temporary anode that is shorted to the structure being tested. This will result in very large current surges that can cause injury to personnel and damage to equipment. When conducting work on or near circuits, energized lines, or parts of equipment operating at or above 50 volts, utilize work practices that are approved from a safety standpoint. For existing metallic structures such as metal fences, culverts, abandoned pipelines, or abandoned wells can be used as temporary anodes or to supplement installed temporary anodes. If any existing structure is to be used, it should first be tested to see if that structure is shorted to the structure to be tested. The area of the temporary installation should be well scouted to determine if any possible temporary anodes exist or if any foreign structure is in the area. Do not use pipelines or tanks for temporary anodes that would be adversely affected if leaks occurred. Okay, I'm looking at my clock now, and we didn't get quite to the end of our slides here, but we do need to bring things to a conclusion here. So anyway, this is a lot of highly technical material, and you certainly cannot be expected to absorb it in this brief presentation. But I would suggest to you that you get a copy of these PowerPoints and studying them at your leisure, because there's good information on here, but it takes time to absorb it. With that, since I don't like to keep people after school, I'm going to thank you very much for letting me chat with you today. And now I'm going to close things out and wish you all to have a nice rest of the day. Thanks a lot. Bye.